What's up, Raiders? We're going to take a look at a level 2 pulley scenario here. And what you're going to see is that this follows pretty much the same steps as a level 1 pulley problem. It just happens to be a little more elaborate because now instead of both blocks being hanging freely down, one of them is resting on a table. So that adds in an element of friction. And you can see I've indicated the coefficient of kinetic friction between the block and the table is 0.25. So we can just kind of assume that once you set this pulley system up and you give it a little nudge to overcome that greater coefficient of static friction, then from there, as we're analyzing its motion, this is going to be the degree of friction that we're going to deal with at 0.25. So similar to a level 1 pulley problems, the starting point here is to calculate the acceleration of your system. And then from there, it's an easy enough substitution to figure out what's the force of tension, how much tension is in the string. And then a one-dimensional motion question I could ask you could be something like, if this hanging block hits the ground moving 6 meters per second, how much time was it dropping before it hit the ground? So just like with our level 1 pulley scenarios, we're going to identify the direction of motion as being positive. And then we're going to draw a free body diagram showing all the forces acting on both of the blocks. So we'll start with the easier block, the one that's just freely hanging here. So for this 10 kilogram block, that mass, the force of gravity, the force of its weight, whatever term you prefer, you take its mass in kilograms, multiply it by the acceleration of gravity it's subjected to, so 10 times 9.8. So the weight of this hanging block is 98 newtons. And that block is kept from just plummeting down in free fall by the tension, the force of tension, from the block on the other end of the pulley system. And this is our free body diagram showing all the forces that are acting on the hanging block. And now I'm just going to kind of put a little reminder for myself that, all right, I previously had said that we're going to make the direction of motion positive. This 10 kilogram block is moving downward. So in a minute, when we apply Newton's second law here, F net equals ma, downward quantities are going to be positive. So let's apply Newton's second law here, F net equals ma. And in this case, both forces that are acting are in the line of motion, so they're going to be included. Since force is a vector quantity, direction matters. You only worry about forces that are in whatever particular line of motion you're talking about. So the force of tension plus the force of weight, collectively those two forces, when they're combined, are going to make this 10 kilogram mass accelerate. And just remember, big picture, we already know when we ultimately calculate this acceleration, it needs to be less than 9.8, because no matter what, the block in this table at least holds back the other 10 kilogram block at least a little bit from free fall. So no matter what, if we've done this problem correctly, this acceleration value should be something that is positive, because we said the direction of motion is positive, but it should also be less than 9.8 because it's got to be less than free fall. So now that I've just generically identified the forces that are my net force and that they're being combined, now I'm going to take into account direction, since force is a vector quantity. Well, the force of tension holding the block back is against the motion, so that's going to be negative. And the force of weight of the block, that's in the direction it's moving, so that's going to be positive. So negative Ft plus 98 equals 10a. So notice we can't solve this equation here because we have one equation, but two unknowns. We don't know the force of tension, and we don't know the acceleration of our system. So in and of itself, we can't solve this equation. So we're kind of stuck in the moment, but now let's draw a free body diagram, show all the forces acting on this block, and then we'll apply Newton's second law to that and see where that can take us. So this one's going to be a little more complex because there's going to be more forces acting. So for the block that's on the table, so again, the force of weight going down, we already calculated it. Mass times gravity, 10 times 9.8 is 98 newtons. Now, the difference here compared to this block is that the one resting on the table, the weight is pushing directly down on the table. In response to that, the table pushes back with a reactionary normal force, and it's going to be equal and opposite to that weight, so it's going to be 98 newtons. And the force of tension is pulling this block on the table to the right. Now, in response to that motion, friction always resists motion, so the force of friction is going to the left. And now we can calculate the force of friction that we're going to be dealing with here. Force of friction equals mu times the normal force. So in this case, 0.25 times the normal force of 98 newtons. So we get 24.5 newtons. So if we just stop and reflect for a minute on what this really means for us. 0.25 is the coefficient of friction. That indicates the level of friction that exists between the block on the table and the table that it's sliding on. So if you convert 0.25 to a percent, that's 25%. So what that really tells you is when the block is in a kinetic condition, when it's sliding, that the friction force is going to be about 25% of that normal force pushing the surfaces together. And that's ultimately why this pulley system is still going to accelerate, because even though the masses are the same, only about 25% of the weight of this block is going to factor into friction, holding back the hanging block. So now I'm going to apply Newton's second law to this block, F net equals ma. Now, remember, force is a vector quantity, direction matters. So if you look at our free body diagram, yes, there are 4 forces acting, but you only concern yourself with the forces that are acting in the line of motion. So that since the line of motion is horizontal, these are the only ones we have to worry about. And I'm going to draw my little reminder arrow for myself that we had previously said the direction of motion was positive, and this block on the table is moving to the right. So anything going to the right is going to be positive. So with these two forces, we've got the force of tension plus the force of friction. Those two forces, when they're combined, will be responsible for this 10 kilogram mass accelerating. So the force of tension, we don't know what it is. The force of friction, we do know what it is. So we've got the force of tension plus, now the force of friction is against the motion, so that's going to be negative, so it's going to be plus negative 24.5, or just force of tension minus 24.5 equals 10A. So notice we still can't solve this equation. One equation, two unknowns. We don't know the force of tension, and we don't know acceleration. However, these two blocks are connected to the same rope. So the tension in the rope is going to be the same everywhere. So the tension on this side of the rope is going to be the same as the tension here. So what that allows us to do is take our two equations that we created, rearrange them so that we can get expressions for force of tension, and then we can do substitution, solve them as a system. So I'm going to rearrange this equation to express it in terms of force of tension. So I'm going to add 24.5 to both sides. So an expression for the force of tension for the block on the left is that it's equal to 10A plus 24.5. Again, we still can't solve it. We still have the same situation, one equation, two unknowns, but at least now we've written it in terms of force of tension. Now we're going to do the same thing over here. Now it's negative Ft. So I'm going to add force of tension to both sides. So 98 equals 10A plus the force of tension. Subtract 10A from both sides. So 98 minus 10A equals the force of tension. Here's another expression for force of tension. And again, in isolation, this equation, you can't solve it by itself. One equation, two unknowns. But again, this force of tension right here is the same as this force of tension right here. So the force of tension on the left side of the pulley equals the force of tension on the right side of the pulley. So now we can substitute our expressions for force of tension in here. 10A plus 24.5 equals 98 minus 10A. And by doing the substitution, now we have one equation and one unknown, so we can solve for our acceleration. So now I'm going to solve this equation, add 10A to both sides. So 20A plus 24.5 equals 98. Subtract 24.5 from both sides. So 20A equals So 98 minus 24.5 is 73.5. So 20A equals 73.5. Divide both sides by 20. So the acceleration that we get for this pulley system is 3.675 meters per second squared. And again, just reflecting on this value, it should be less than 9.8. And sure enough, it is. Because no matter what, this block on the table holds back the hanging block at least a little bit. That's why the acceleration has to be less than 9.8, and it should be a positive value, because earlier we identified our direction of motion as positive, and obviously this block's going to accelerate downward. So that checks out. Now the next thing we're being asked is what's the force of tension in the string? And that's easy enough. Once you've done all this hard work to calculate what the acceleration of your system is, now you can just do a substitution. Take either of your force of tension expressions. It doesn't matter which one you use. So I'll just take this one on the left here. Force of tension equals 10A plus 24.5. Well, the acceleration is not unknown anymore. We can substitute our acceleration of 3.675 in. So the force of tension is going to be 10 times 3.675 plus 24.5. So that ends up being 61.25 newtons. That's the tension in the string. So if the manufacturer indicated that the rope had a tensile strength of 60 newtons, this would be too much tension, the rope would break. But if the manufacturer reported the tensile strength of the rope as 70 newtons, then you'd be okay. So now the last part we're going to solve here. If the hanging block hits the ground moving 6 meters per second, how much time was it dropping before it hit the ground? So one thing you have to infer here, but it's a reasonable assumption, is that when you're in the process of setting up this level 2 pulley system and you're tying, each block onto the rope and everything, nothing's moving. And then you have to give it a nudge to get it going. And then once you get it going, then you can step back and just let it do its thing. So based off of that reasonable assumption about the scenario, we can say the initial velocity is 0. In the acceleration, we didn't know what it was before, but we do now. So the acceleration of our system is 3.675 meters per second squared. And when we were told that the box hits the ground going 6 meters per second, I know sometimes a natural tendency for a student to think is, oh, the block hits the ground and stops, so final velocity is 0. But remember, we're analyzing its motion in the air. So we would call this the final velocity is 6 meters per second, not 0. Because when we say the final velocity, as we're analyzing the motion, we really mean the millisecond before it hits the ground. How fast is it going as it hits the ground? So we know VI, we know A, we know VF, and we're trying to find time. How much time did it take for it to hit the ground? So if you look at that combination of variables, that's going to set up for using the equation VF equals VI plus AT. So substitute your values in. It hits the ground going 6 meters per second. That's the final velocity it ends up at. It started from rest. It started at initial velocity 0. And then if it's accelerating 3.675 meters per second for a certain amount of time, it's going to hit that velocity of 6. So divide both sides by 3.675. So the time ends up being about 1.63 seconds to hit the ground. All right, Raiders, as always, if you have any questions, you know how to get a hold of me.